Good evening, everybody. This is Mr. Steele. I'm coming to you once again from the desk at my house where I make these standard quiz videos where I explain things that hopefully you do know, you just need a refresher on, and I do examples to help you so that you'll be better prepared for the standard quiz questions that we face every week on Fridays and or Thursdays and an occasional Tuesday when the schedule calls for it. So today I'm hitting at the third most important standard that people have been missing consistently, and that is once again another one from pre-cal, another one that you've already kind of seen before. It was on last year's term 2 or term 3/4 honors pre-cal standard quiz, and that is solving trig equations. So trying to take a trig expression, set it equal to 0 or whatever it's set equal to, and then solve it and figure out what values and what angles you could put in to make the equation true. Simple as that. Before we start though, before I start going through some examples, and oh, do I have examples for you. I mean, look at all those things. Like, there's 4 big examples here that I'm going to go through that kind of hit all the important ideas and concepts. But again, before I get that, there's stuff that you just plain old need to know. Like, there's just some pieces that you just have to have in your brain. So just to kind of remind us what it is as I'm talking about this first part, I'm just going to remind you what it is that your brain is. It's that thing that's stuck inside your head. Otherwise, your skull would be open. It'd be nice. But these are all the things that I write over here that you just need to have in there. Like, they're basic prior knowledge that you should have. So some of those concepts that you really need to know are, of course, the unit circle itself. Knowing information about the unit circle, and in particular ASTC, so all students take calculus, what the positive and negative signs, SIGNs, are for each of the trig functions in those places. You also need to know plenty about special right triangles, particularly, well, there's 2 special right triangles that we prize above all others. That are the 30, 60, 90 right triangle, which has the ratios as such, and then of course the less heralded 45, 45, 90, just because it's less entertaining because it's isosceles. So we all have a bias against isosceles triangles. Of course, that's the other piece of knowledge. What else do we need to do? We need to be able to do really good things about knowing basically how to construct it, where the values are, and about stuff like period. Like the period of a sine function or a cosine function or a tangent function. Any of those things, we need to be able to analyze the period because that'll help us determine information. And last but not least, we need to know algebra, and we need to have pretty much flawless algebra skills. Because if we don't, no matter how much we know about this, and this, we're still going to screw up and fall flat on our face when we go to actually do problems. So here, all these things, they're stuff that should just be in your brain. Like, they should already be there, in fact. So maybe it'd be good to include the word already. But basically, now that we've kind of thrown those terms and ideas out there, let's actually go and tackle a problem. I mean, why not? That's the whole reason we're sitting here watching this video. Okay, so the first thing I'm going to do before I start this first wonderful trig problem is I'm going to emphasize that there are always 2 different ways we could ask for your answers on the standard quiz, as well as in real life when you're actually doing a problem on a test or a quiz or on an AP test. And that is, we could ask for you to just tell us the answers or solutions on a small interval. Usually we go 0 to 2 pi because that's 1 full period of the traditional sine cosine function, the parent graph, if you will. Or we could ask you to give us all the values where all the angles or x values where it makes it true over the real numbers, in which case we'd want every single possible value that could work. Or since we don't have an unlimited amount of time and you don't have an unlimited amount of lead, we just want some expressions that represent ways we could find every single possible solution that we could get. So for each of these problems, assuming I don't forget as I go through, I'm going to actually go through and find it first on 0 to 2 pi, which is always easier, and this is a traditional question, and then I'm going to find it over the reals, mostly because I enjoy doing this. I am, in fact, a trigophile. Like, I love doing trig problems, and I was really jealous of all the honors pre-cal kids today in math lab that were doing trig problems when I just got to sit back and watch and feel bad. So where we're going to start? We're going to start with a fairly simple trig function right here in terms of cosine. 2 cosine squared of x plus cosine of x minus 1 all equal to 0. So when you look at this, of course, the first thing you might see is that, well, there's a lot of stuff going on here. Like, we've got cosine squares and cosines minus 1s, but hopefully what you think of in your mind is not necessarily a trig thing, but just like a polynomial thing. Like, hopefully you think in your head, gosh, Mr. Steele, this looks a heck of a lot like 2x squared plus x minus 1 equals 0. And you know what, you'd be right, Timmy, or whatever your name happens to be. This does look an awful lot like it. So what we're going to start with is we're just going to kind of pretend that it was and factor it down so we can get to a point where we really have a trig equation or 2 that we can solve. So to factor this guy, basically I do the diamond. You don't have to do the diamond. You can probably do it in your head at this point in your math career. But basically I want to know what 2 numbers multiplied -2 add up to 1. It's going to be +2 and -1, and that allows me to split the middle, if you will, or do the box, however you like to do it. And that's going to give me this expression, which is all equal to 0, or so an equation overall. From here we can factor it. I can pull out GCFs right and left, And what I will eventually get is, and basically again I've got to be a little careful here as I do this, and again this is all in quotes because it's all faking it, we're cheating here, this isn't what the equation is. We end up getting 2x minus 1 and x plus 1 equal to 0. Well, now remember, that was just the factoring step. Basically, we are in terms of cosine, so we need to convert this back to the actual problem that we have. In particular, this is really 2 cosine of x minus 1 times cosine of x plus 1 equals 0. This is actually our problem. This was all just make-believe. This is like unicorns. These do not exist. This is just us cheating. It's like, you know what, I don't understand a unicorn, I understand horses with horns, so I'm just going to imagine a unicorn as a horse with a horn. See? Blew your mind right there. You're welcome. So from here, what do we do? Well, basically we now have two possibilities. The zero product property, as you learned back in Algebra 1, says that if two things multiply to 0, one or both of them has to be 0. So we get two possible ideas. We could have that 2 cosine of x minus 1 equals 0, or we could have that cosine of x plus 1 equals 0. And of course we have to check both possibilities, because otherwise we'd be an incomplete mathematician. So for each of these we have a trig equation. We have 2 cosine of x minus 1 equals 0, or cosine of x plus 1 equals 0. What can we do from here? Well, first of all, I'm going to convert it by doing algebra. On this side, the one with the little star I just drew and I erased, I'm going to add 1 and then divide by 2. I'll get my trig equation to solve is cosine of x equals 1/2, and I like to actually include the sign, just because that reminds me about ASTC. Over here I'm just going to subtract 1. I'm going to get cosine of x equals -1. And now we're at the point where we go, okay, now I've got to actually start solving some stuff. I've got to find actual angle values here. So to do this, I'm just going to look at each picture individually. For this first half, I'm going to go, okay, fine. You tell me cosine of x equals positive 1/2. I look at my picture, and I use ASTC. And I say, okay, if cosine is a positive number, cosine, the angle has to be over here in quadrant 1, or over here in quadrant 2, or 4. This side doesn't give me anything because cosine's negative over there. And if cosine of x is equal to 1/2, we have to have 1, 2, and root 3. Same thing on the bottom as well, except one of these things, a couple of these things would be negative. Well, what does that tell me? Well, this tells me what kind of reference angle I have. If we're opposite the root 3, that means my reference angle, again, you don't have to write this is all stuff that you're doing in your head. For right now, I'm writing it down as we go. My reference angle has to be 60 degrees, which in, radian terms, is pi over 3. So this tells me that I have a pi over 3 reference angle over here, and judging by the quadrants I'm in, that's going to give me pi over 3 for the angle in the first quadrant, and then 5 pi over 3 for the angle in the last quadrant. Is it the same thing as negative pi over 3? Well, sure it is, but of course we want to go between 0 and 2 pi, so we should write it as 5 pi over 3. On this side, cosine equals -1. Gee, let's do that stuff again. So we'll draw a picture. Well, cosine's negative, ASTC. That means it can't be over here because we just said cosine's positive over there. But if it's -1, that tells us that we actually have to be at one particular point. There's only one possibility here, and that is right here. Like, this is the only place where the cosine is actually -1, because -1 is the minimum value of cosine. What that means is then we have only one answer, x equals pi. And so what we've come up with are 3 solutions. Like, should we expect 3? Well, maybe not, depends on the situation, but for now 3 works good. So to answer A, if we're trying to solve this trig equation, this one right up here, if we're trying to solve that guy over 0 to 2 pi, we've found our answers. Typical order is to just write them from biggest to small, or smallest to biggest. So we have pi over 3, comma pi, comma 5 pi over 3, and we are done. We have now solved this trig equation. So, what does that do? Well, that's great. We've solved it. We found the 3 values where it works. But of course, that's not sufficient. We want to actually do one more thing. We want to go through and actually find what are all the possible values that could work for solving this trig function. Like, what is every possible angle that we could get? How could we find those angles if we wanted to? And basically the way we do that is we exploit the fact that sine and cosine and tangent, all those guys in the trig family, are periodic functions, meaning that they repeat itself. Like, think about just a picture in your head. Like, what does cosine look like? It looks like this. And then it keeps snaking up and down, 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 up and down. It just keeps going. Well, it erased itself. That's nice. It keeps going back and forth because it keeps hitting those same values again. Cosine goes from -1 to +1 all the time. So in other words, basically, if we have 3 distinct values, we can find all the values just by adding a period to it over and over and over and over again. So here's how I think you could probably write these answers. Like, we can do the x equals, and then we write our 3 values. But we leave some space because we're going to need to indicate that we're going to add the period over and over and over again. Again, on a standard quiz, you've got answer line for this. There's room. So here are our 3 original answers. Now we're going to adjust for adding a whole bunch of periods. So add whole bunch of periods. Now some of you are thinking you're funny, and you're going, I'm just going to include ellipses. And you just kind of do this. Well, yeah, that is a whole bunch of periods, but you're not really that funny, and grammar jokes really don't work that well. So instead, what I'll point out is that if we want to add a whole bunch of periods, we just have to first of all know what the period is. So if you look at both of these functions, they're just like the parent ones. In fact, it is the parent one on the left side. So our period is just 2 pi over 1, which equals, last time I checked, 2 pi. So to do this, we're going to add 2 pi to each and every one of these guys. But of course that would just give us 2 more answers, and since we didn't write them again, that would actually only still give us 3 answers. But we need to indicate that we could add 2 pi any number of times, and heck, we could even subtract it if we want to. So to indicate that, we say, okay, we're going to add plus 2 pi k to each one of these guys. What does k mean? K is an integer. And there is another notation for that that's saying k is a member of like a big bold scripty z. But in fact for here I think it's easier just to describe exactly what it is. We're saying k is an integer. So if we want to find more answers, we can make k say 13, and then we could add 26 pi to each of these answers and we'd get some. If we want to make it k equal 42, we can get some more answers that way. We could even add k equal -7 and we could get more answers. And there we go. We've now found a way or an expression to calculate all the possible angles that would solve this original equation to cosine squared of x plus cosine of x minus 1 equals 0. We've found them all. The red ones were the original solutions on 0 to 2 pi, and the green ones were the ones that were over the reals. So these are a complete, totally nice answers. So voila, we've solved our first trig function. Okay, we've now got one problem out of the way. We've seen some trig solving in action. We've used ASTC and a bunch of other and special right triangles, lots of cool stuff, and we were able to solve a trig equation, a fairly complicated one that was in kind of polynomial form, over to 0 to 2 pi and over the reals. So we've done some good stuff. Let's keep going though. Now we want to solve the equation 2 sine of x secant of x minus sine of x equals 0. The first thing that you hopefully see here is, well obviously hopefully you see a trig equation, because if you don't you might want to consult your optometrist because it's important that you can actually visually see what's happening. But second, the other thing that I hope you see is that in fact there's a GCF sitting in here. And of course factoring is usually a great strategy to start an equation because you break up a more complicated picture into something a lot smaller. So in this case the first thing I'm going to do is I'm going to pull out that GCF. I've got a GCF of, oh you can't see that. I've got a, no you don't have a GCF of, no I can't see that. You have a GCF of sine of x. So if I pull out sine of x, I can rewrite this as then what's left? 2 secant of x minus, well if I pulled out sine of x I've just got a 1 left over. So now we've got this equation to work with. Why is that valuable? Now we've got a product of two things that's equal to 0. Oh look, it's the zero products property once again. Gosh, that thing doesn't go away. So what does that give us? It gives us two possibilities. Either sine of x equals 0, because the first thing could be equal to 0, or 2 secant of x minus 1 could equal 0. One of those things is true, maybe both of them, we don't know yet. From here, obviously this isn't enough. I've got the sine of x equals 0 part, that's great, but over here I'm going to add 1 and divide by 2. I'm going to get that secant of x equals positive 1/2. And so now I'm ready to start solving. So I'll switch to red pen color. And then let's actually look. Let's look at the first one. First of all, sine of x equals 0. So if we think about ASTC, and we use what we know about the intermediate value theorem, because see, it's calculus. Think about that. If we want to find where sine of x is 0, we've got to find a place where sine goes from positive to negative. So sine goes from positive to negative, or negative to positive, right here and right here. Since we know sine is a continuous function, you can't forget that. That's the first assumption of intermediate value theorem. So know it's one of those two places. What are those two angles? Well, since we're going from hard bracket 0 to comma 2 pi soft bracket, we can write those two angles as 0 and pi. Because again, 2 pi is there, but 2 pi is not in our interval. So for the first part, that's not going to be necessarily relevant. We can find that by adding 2 pi k later on. So for the second one, though, we've got to do a little bit of work. I haven't memorized the values of secant, or well, actually I have, but I mean that's beside the point. You probably haven't memorized them because no one really asked you to memorize secant. Secant's kind of one of those oddball guys, like your great uncle Norm that shows up every other family reunion and eats a lot of of the tofu dishes. Secant's just one of those other guys. So instead, what I like to do is I like to think to myself, how can I relate secant of x to something that I care about? Well, secant of x is really equal to 1 over cosine. So that means that 1 over cosine of x is equal to positive 1/2. Well, that's kind of crappy. I don't want to solve that. Instead, you could think of it as taking everything to the negative 1 power, like basically taking the reciprocal of everything, or you could think of it as just flipping both sides, or cross-multiplying, however you do it. This gives us an equivalent equation that cosine of x equals positive 2. So we've just got to find all the places where cosine equals positive 2, where the adjacent side over the hypotenuse is equal to 2. But there's a problem. Cosine. Think about cosine for a second. What does that graph look like? The parent graph goes like this. The maximum value is positive 1. The minimum value is negative 1. 2 is up here. That means there is no value. There are no x's that make cosine equal to negative 2. At least not in this universe, or multiverse, depending on how you want to look at it. So in fact, there are no x values that solve this part. So this entire half of the equation is basically moot and worthless. Like, we don't even have to worry about it. Our only solutions are going to come from right over here. X equals 0, comma pi. So we go, okay, let's get started here. What are my answers? Well, first, on 0 to 2 pi, we already know that x is going to equal 0 or pi. Those are our only two options because they're the only places where some part of this equation can equal 0. So lovely, we've got those two. Now the question is, how is it that we can go ahead and find the second part? And actually, I should go back and very quickly add in my little star to indicate again that's what we got in the red, was we found the solutions on 0 to 2 pi. Next, we said let's look at the green and let's figure out, okay, so what are the solutions over the reals? What are all the possible x values that we have? Well, let's think about it. The last time we said, okay, it's equal to 0, comma, pi, and then we added plus the period times k. Well, the period, once again, for the only half that matters for sine, is 2 pi over 1, otherwise known as 2 pi. So it might seem like you can just go, oh, 0 plus 2 pi, pi plus 2 pi, and then we add the k to say that, well, whenever k is an integer, we can add 2 pi and we can get back to our answers. This is a correct answer. There's nothing really wrong with this, although it's kind of redundant to write a 0 plus 2 pi k. That'd just be 2 pi k. In reality, though, what you might notice is that if we think about all these answers, this would be all the even pi k's. So think about it for a second, or all the even pi's, like all the answers we'd get. If we add 2 pi to 0, we'll get 2 pi. Add 2 pi again, we'll get 4 pi. Add 2 pi again, we'll get 6 pi, 8 pi. We could keep going on and on. We could even get 42 pi if we wanted to. And in fact, this is just giving us even pi's. Over here, though, pi plus 2 pi would be 3 pi, 5 pi, 7 pi, 9 pi, ... 117 pi would eventually show up, ... What we're finding over here are all the odd pi's. So in fact, these two things are basically saying, if we have any multiple of pi, including 0 and including negatives, because we could go backward if we wanted to, basically any multiple of pi, we have an answer. We have a solution that works. It's just going from 0, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi. Or if we went backwards, negative 1 pi, negative 2 pi, negative 3 pi, negative 4 pi. Basically any pi works. So instead of writing this answer is correct, but unfortunately it's redundant. So redundant just means it's repetitive. Like it makes you look like a noob. It makes you look like you don't understand how trig stuff works. So instead, we can solve that by saying, well, basically, we just want any pi k. So we can instead write it as either 0 plus or just pi k for k being an integer. And that is the simplest, bestest, is that a word? I'm not sure, possible answer that we could give. This says any multiple of pi, what do you call it, any integer multiple of pi or integral multiple of pi will give us an answer that works. And again, we're there. Nothing's happened. Nothing scary whatsoever in doing this problem. I mean, I can't imagine being scared by this problem at all. I mean, it's not like there's anything scary on the screen that's staring back at you, ready to jump out of your screen or cell phone and tear your body apart and scare you to death. Nothing like that at all. So hey, we've solved 2 trig equations. Good for us. And onward to problem number 3. So this is the problem that I think that we really separate the hamsters from the Tyrannosaurus rexes. Like, this is the problem that really shows me, do you understand this concept and the ideas and everything that comes into a trig function, or are you just kind of faking it as best you can and trying to look at your calculator to find some answers? So, very tough, very real question. So again, we're going to solve this equation. 2 sine of 3x plus root 3 equal to 0. What I would hope you notice first before anything else, aside from that there's a trig equation here, is that inside here we now have something changed. Every other problem so far has had just plain old x's on the inside. So plain old x's, plain old x's. Like there were weird things happening outside, but there was just that plain old x on the inside. So this is our first one, which has like a period shift. Like this means that basically the function's repeating itself way quicker than it was before. So we'll have to account for that in our answer. And some of you will know very quickly to say, well, this is going to triple how many answers we have in all likelihood from what we would originally have. To start out with though, basically doing this problem comes down to just basically pretending like nothing is amiss. There's nothing strange happening in this equation whatsoever. So my first thing would be to do the subtracting of root 3 and then dividing of 2. Like if I do just the plain old algebra, that's going to give me sine of stuff equals negative root 3. Why sine of stuff? Well, you'll see soon enough. Just patience. Patience, young Padawan. So what do we have? Well, let's see here. We would need to find where sine is equal to negative root 3 over 2. Well, ASTC. All students take calculus. That's exactly what I was going to say was calculus. So ASTC. So what do? Well, we were trying to find where sine could be negative. Well, sine's positive, and all are positive up here, so failure you. Instead, our angles have to be down here and here. What else do we know? Well, if the sine is going to be negative root 3 over 2, it has to be opposite over adjacent, or hypotenuse, opposite over hypotenuse, and that means that once again we're opposite root 3, which means that we've got 60-degree reference angles. Again, this is all something that can happen right in your heads. Like you can do this all in your head without doing any bit of work. I just show work so that I can help you illustrate what it is that I'm doing and thinking. Otherwise, I just look like a math magician. I think that's already a word that's copyrighted. Otherwise, trademark me. Okay, so what do we have? Well, it turns out that whatever's on the inside, whatever that angle has to be, is going to be equal to one of two things. Like from here, we've got one possibility over here. Reference angle is pi over 3. That's going to give me 4 pi over 3. Or the other possibility is going to be that it's over here, which is 5 pi over 3. Like basically, I get two answers really quickly, and you're like, okay, let's go over and write answer A. No, wait. That's not it. Remember, inside here, we didn't just have x. We had 3x. So we've actually just found what 3x would be equal to in this perfect happy world. Like that's it. What do we need to do? Well, we want to find x. What is x equal to? What's the actual angle I have to put in here? So to do this, we're going to go on to both sides, basically this entire equation, and we're going to multiply by 1/3. We're going to basically, it's a terrible 3, I'm embarrassed and ashamed of it. We're going to multiply both sides by 1/3. What's that going to give me? Well, for one thing, it's just going to tell me what x is. It means x is going to be 4 pi over 9, and x is going to be 5 pi over 9. These two angles are actual solutions to my problem. I can actually plug in 4 pi over 9. That will give me a true statement up here. It'll make the whole left side equal 0. So good for us. We found two solutions. Now I get to go write it over there. But wait. Remember, sine of 3x. What does that mean? Well, think about it for a second. Sine of x is this guy. It's odd. And it basically repeats every 2 pi. You get the whole shape. You start at 0, come all the way down and up, you get that whole little squiggle, and it goes to 0 to 2 pi. Sine of 3x, though, is different. This thing is repeating 3 times as quickly, meaning its period is 1/3 of what it was before. In fact, if we do the typical period calculation, it's going to be now 2 pi over 3, because, we have that 3 in front of the coefficient. It's, basically moving things around that much quicker. So what does that look like? Well, think about the picture. On 0 to 2 pi, if we go the same distance here, instead of just going like that, as we get up to 2 pi, this time it's got to go 1, 2, and 3. It's got to hit 3 times. And that means that we're going to have 3 times as many solutions over here. We're not going to have 1, 2, 3, 4, 5, 6 solutions. They're going to repeat all that more often because the period is that much shorter. So the question you might ask yourself then is, how do I get all my answers here? How do I find all the possible solutions? So again, because we're trying to answer A, what are all the numbers, all the angles between 0 and 2 pi that make this equation true? Well, first of all, we got 2 of them. We got a couple. We got 2. We got 4 pi over 9, and we got 5 pi over 9. Great job, everybody. That's a terrible 9. Becoming a perfectionist on these things. There. We've got those guys. But how do we find the other ones? Well, basically we use the fact that it's going to repeat again every period. Like we basically will add the period to it. So for this first one, we'll add 2 pi over 3. Oh, but you know the problem? Oh man, we're going to add a period over here. So let's start this again. So we're adding periods, because that'll cover all our repetitions. The problem here is 2 pi over 3 and 4 pi over 9 is the common denominator's issues there. So let's first find the common denominator for this guy. Let's write it so it looks like 4 pi over 9. This is going to be 6 pi over 9. And so now we can add our period. We'll add our period for the first set of repetitions. Like basically right now we've got the first one and the second one. Now we're trying to get third one and fourth one. So we add 6 pi over 9 to both of those first two angles, because each one is going to repeat in 2 pi over 3. What does that give us? That's going to give us, I shouldn't do those lines, squiggle it. That's going to give us 10 pi over 9 and 11 pi over 9. So there are our two second answers. We've got this guy and this guy. That's a terrible dot. And so now we can add two more up here. Are we done? Never. We're never done. Well, we'll be done with this problem eventually, but for now we're not done yet. Because of course we haven't found all the solutions. We've only got 4 out of the 6 that are going to come up. So how do we find it again? Oh, I don't know. How about we add the period again? We just do it again to cover that extra repetition. Plus 6 pi over 9, plus 6 pi over 9. That's going to squiggle me to 16 pi over 9. And adding 6, 17 pi over 9. And there are all our answers. So we've got, in fact, 6 whole answers. And this is a completely reasonable question to ask on a standard quiz because the process is so similar. It's so straightforward to go through. Like, you just have to understand some trig stuff. Now, someone, before we go through and do over the reals, someone might be asking themselves, wait, how do you know that you've got to stop there? Well, what I might submit to you is that we're talking on 0 to 2 pi. And 2 pi is the same thing as, in terms of like our common denominators there, as 18 pi over 9. So we want to stop as soon as we hit 18 pi over 9. Or anything close to it. We can't go past it because that would take us outside of this interval. Well, if you look, if we added 6 pi over 9 again, we'd have 22 pi over 9. That's too many pi's over 9. We'd have to have 18 or fewer. We'd actually have to have fewer than 18 over pi over 9s. So in fact, if we went any bigger, that would be wrong. So in fact, we're done. We've found our 6 solutions, and that's exactly what you can expect in a situation like this. Now, this is what's cool. Usually, when we get to the over the reals part, the answer looks way more complicated and longer than each of these things. And so you might be thinking in your head, okay, I'm going to have to go 4 pi, you're going to go, I'm going to add 2 pi k up here plus 2 pi k up here. But in fact, and then you have to do it some more here and here, maybe a little bit here, not there, here. I'm trying to find the right spot. I'm so excited trying to do this voice. And here, and you go, okay, I've got to write 6 times 6 different angles plus 2 pi k. That is ridiculous, Mr. Steele. That is ridiculous. Certain one of my students that's in Arts Pre-Cal right now would roll her eyes and glare at me if I made her do that. Well, obviously then, this isn't a realistic way to do it. Instead, I submit to you that there are 2 things wrong with this. First, when we add 2 pi k, that's because the period is 2 pi. It takes 2 pi to repeat. Over here, though, our period is not 2 pi. It's 2 pi over 3. So the first thing we'd have to do is we'd have to add our new period, because it's repeating that much quicker. So on each of these, we would go, okay, plus 2 pi over 3k, plus 2 pi over 3k, plus 2 pi over 3k. Okay, you say, that's even worse than before. Now I've got to write plus 2 pi k over 3 6 times under my answers. So you would be right, if not for the fact that there's some symmetry here. This thing, when we say an angle plus 2 pi k, or plus 2 pi over 3k, we're saying add 2 pi over 3 to get the next angle. But we already did this. This was adding 2 pi over 3. We added it for when k equals 1. Then down here, when we added 6 pi over 9, we added, once again, 2 pi over 3. So we've already done that. Like this angle, this angle, this angle, and this angle are related to one another, to our original 2 angles, by adding that period of 2 pi over 3. So in fact, for our last piece, for our answer over the reals, we don't even need to include those guys, because those are just included repetitions. Writing this would be redundant, and it would again make you look like a noob. Instead, what you can do is you can just write the original 2 and say, okay, my 2 answers here, 4 pi over 9, comma, 5 pi over 9. And then to get all these other answers plus every other one in the universe, I just need to add my period, which we could write as 6 pi over 9, but again, that's not necessarily as pretty as it could be. 2 pi over 3 is the simplified form. So I'm going to add my period, and then multiply it by an integer to see how many times or whether we want it positive or negative. And of course, what is k? K is an integer. It's something like -7 or 42. And so actually, in this case, for once in our lives and in our standard quiz, writing out the over-the-reals answer is actually shorter than writing out the answer for the original one on 0 to 2 pi. So there we go. This is the period shift problem. If you really understand what cosine and sine are doing, what those parent graphs are doing, and you understand what it means to be a period and what that repetition tells you about the values of sine and cosine, this is a breeze. You still have to write a lot, and you still have to do a little bit of work, but now that you've got this, you should be able to approach the problem pretty easily. And again, this is my favorite. This is a Mr. Steele favorite. So I love these problems. If I have my way, maybe we can throw this on the final or something like that, because this is good stuff. So you've now seen 3 different kinds of trig functions. What could be left? Well, actually, the 4th one's going to be a letdown compared to this awesome problem. Well, here we are. We're on problem number 4. You know, it's been a great run. You know, I've really enjoyed this standard quiz video so far. It's been probably my favorite so far out of all the ones I've ever made. So I might get a little sentimental as we move forward. But again, wanted to make sure I hit on a little bit of everything here, and so far I've stick to kind of sine, cosine, or even secant, which is just a reciprocal of cosine. So I felt like, you know what, I've left tangent out of this standard quiz video. I want to hit tangent a little bit, and there are some little variations that I haven't hit before. So I want to go through and actually solve this last trig equation just for old time's sake, and figure out when is 3 times the tangent squared of x minus 1 equal to 0. That's my goal. That's what I'm looking for. So first of all, let's go through and do some algebra here. And you might be tempted to do some difference of squares action here, and that would be one strategy. I prefer, though, going through and very carefully basically solving for the trig function as best I can. So the first thing I'm going to do is I'm going to add 1 to both sides and then divide by 3. So I'm going to get tangent squared of x equals 1/3. Next, I'm going to go ahead and square root both sides, because that's what I do when I see things that are squared. So I'm going to end up with tangent of x equals square root of 1 is 1, square root of 3 is root 3, and then of course since I put the square root in there, I'm going to have to include plus or minus, because positive or negative answers will both work at this point. So without rationalizing, I've got the tangent of x equals plus or minus 1 over root 3. So now I go to my ASTC. I think about, okay, where could my angles be, my tangent be positive or negative? Well, let's see. All students take calculus. They take calculus. So what do we have? Well, let's see. All are positive here. Oh, tangent could be positive up here, so we get a triangle. Beautiful. Let's see. Sine is positive, so tangent's negative. Oh, tangent could be negative over here. Down here, let's see. Tangent's positive. Oh, tangent's positive. That's a possibility for me. And let's see. Cosine is positive, so tangent is negative. Oh, that could be a possibility too. So what you see is because of that plus or minus, we actually end up with 4 possibilities. Any of these answers could work. And so the shape we get is kind of a bow tie, like the kind that Ken Rosenthal wears when he's at a baseball game. Now that's easy to confuse. I'm not talking about tie bow. Tie bow is this. That's tie bow. That's Billy Blake. Tie bow is different than a bow tie. A bow tie is something you wear. Tie bow is something you do while watching a video with Billy Blake. So again, we've got a bow tie shape. We've got to find 4 answers here in order to satisfy our 0 to 2 pi. And our period shift, well, there's no period shift. It's just a good old parent graph. So what do we do from here? Well, basically we've got to figure out when is tangent equal to 1 over root 3. What is my reference angle? Because that reference angle will get me each of these pieces. And again, this is all stuff you can do in your head. You can do all this work in your head. Well, let's see. If tangent is 1 over the square root of 3, that means that this is a special right triangle at 30, 60, 90. Again, we're opposite the 1, so that makes this a 30-degree reference angle. 30 degrees is code for pi over 6. So we've got pi over 6 as our reference angle. We've got one of those reference angles in each of the 4 quadrants to give us our 4. So what are they going to be? Well, you know what? I'm going to go ahead and shift to red, since I'm already ready to get my 4 answers in to part A. There we go. So for part A, what am I going to get? Well, I'm going to get x equals. The first one is just the reference angle itself, pi over 6. The second one over here, we've got 6 pi over 6 right here, because that's pi, minus pi over 6 is 5 pi over 6. That's 2. Third one, right over here, 6 pi over 6 plus pi over 6, that's going to be 7 pi over 6. Ooh boy. And And last but not least, it's definitely not the least, it's the biggest angle of the ones we have. We've got one less than 12 pi over 6, otherwise known as 2 pi. That's going to be 11 pi over 6. And those are all our answers from 0 to 2 pi. We found all four. We got it from that bow tie shape, not the tie bow shape. And we are good to go. Now here's the fun part. Well, actually, this has all been fun, Mr. Steele. Like, this couldn't possibly be the only fun part. You're right. For getting it over the reals, we can actually simplify this a little bit. Like, what you might notice is that this guy, I can't draw a straight line even on here. These two angles, the ones that are right there, they basically are along a straight line. They're 180 degrees apart, or otherwise known as pi apart. These two, same dealio. Like, these guys are also that close to each other. So in fact, what we have is we have some symmetry built up. We wouldn't want to go pi over 6 plus the period, 5 pi over 6 plus the period, 7 pi over 6 plus the period, and 11 pi over 6 plus the period just yet, because that would be redundant. We'd be overthinking some of these answers. There's already some symmetry in here. So the first thing that I'll point out when we get there is that the period for tangent is a little bit different. It's pi over the coefficient of x, which of course is just equal to pi. So here, we can think of our period as pi, otherwise known as 6 pi over 6. So let's see, watch what happens if we add our period of pi, otherwise known as 6 pi over 6, to the first one. Pi over 6 plus 6 pi over 6 equals 7 pi over 6. Oh, look at that. Huh, that's interesting. What if we add it over here? 5 pi over 6 plus 6 pi over 6 is 11 pi. Ho, ho, ho. Huh, look at that. We don't really need these guys. If we just add a period each time, in this case the period is pi. If we just add pi k, we're going to get 7 pi over 6 and 11 pi over 6 already automatically. So in fact, those guys are redundant. We don't even need to throw them out there. So in fact, all we need is pi over 6 plus pi k and 5 pi over 6 plus pi k. So let's throw them up here. Pi over 6 plus pi k. Again, it's just period times k. We've got 5 pi over 6 plus pi k. We did need those two because those two didn't have necessarily any symmetry in between them. Then lastly, that's not an effective answer because what the heck does k mean? We need that k is an integer, because that tells us that we can just add or subtract multiples, integral multiples of pi k as much as we want. Again, another notation you might see, that's the same thing as k is a member of the integers. That's how I draw it. Lots of other people have better ways. That's my way. But again, we've solved our problem. We found all the answers in the real world that could ever possibly exist that would solve the equation 3 tangent squared of x minus 1 equals 0. We did that with the same trig tools we've always had, and we did that by thinking about symmetry and period, and of course, actually solving the problem initially. So at this point, we've kind of hit everything. So let's kind of review what we've done so far today, or what we did so far in this video, and then we'll stop, call it a night, because it's 9:47 already, and rendering this is going to take forever. So first, what do? We talked about all the important, basic fundamental ideas that you need. Stuff like ASTC, period, the special right triangles, and the ability to do algebra. All that stuff is in your brain. That's where it belongs. If it's not there, well, the calculator's not good enough. First, we went through a problem where we had to do a little bit of factoring. Then we had some very simple trig equations to solve. Almost always we used ASTC, found our answers specifically, and then of course we added the period times k so that we could go through and basically find all the possible answers. Next, we had one where we again factored, but we ran into a situation where there was actually an expression that didn't make sense, because cosine couldn't ever equal positive 2. That's outside its range. And again, we did everything else the same way. This time we were able to simplify our final answer for the over the reals, because there was some symmetry between the two answers anyway. In this case, we just write it as pi k, so any multiple of pi would work. For the third one, we had a period shift. So that period scrunched in, it became 1/3 the original size because it repeated 3 times as often. So we had to find an extra 4 answers that came from that repetition. We needed 6 total answers. But when it came to writing it over the reals, that period's repetition that we kept adding to get those new answers, well, that actually simplified the problem for us. We just needed our original 2 problems, one for each of the options that would have made sine equal to that negative √3/2, and then we added plus the period times k so that we could get all those other answers included automatically. And finally, in a problem very similar to the third one, but without the super period shift, we had a situation where we had a tangent function where we could have positive and negative answers, meaning that we had 4 possibilities, 1 in each quadrant. We found them all the same way as before, and then we wrote them out. We got 4 answers, and then to write and simplify, we again had some inherent symmetry and stuff, and some automatic answers that came out because we were always pi away with tangent, because tangent's period is shorter. So in fact, once again, we've solved 4 trig functions, 4 very challenging trig functions actually. Well, some of them were super challenging, others were just regular challenging. But either way, at this point, you should be super totally proud of yourself, because this is good stuff, and you've watched a Mondo-long video that hopefully will help you get questions right on the standard quiz. Either way, I'm tired, so I've got to go think up some more problems to... So with that said, once again, this is Mr. Steele. Signing off for the evening. Have a good night, sleep tight, see you in the morning, late start Wednesday, and of course don't let Samari get you. Have a good night.